For today's activity, class activity, we're going to go over chapter 10, sections 6 through 8. Please read those in detail and get comfortable with the concepts therein. And we'll apply them to these concept questions, 10, 11, 12, and 13, and exercises 31, 35, and 39. So go take a look at those and come back to the video. We'll start with number 31. Oh, sorry, we'll start with number 10, the concept questions. Okay, so with number 10, we have this process going on in which potential energy decreases and the system does work on the environment. Okay, so let's write out our energy equation to try and make sense of this. Work external equals change in kinetic plus a change in potential energy plus a change in thermal energy. Okay, and we're told that the potential energy of the system decreases, this goes down, and the system does work on the environment. Okay, so what does that mean about work external? Is it positive or negative? Okay, so work external would be negative because the system's doing work on the environment. Okay, the system's doing work on the environment. So that means this went down. All right, so with that, what happened to the kinetic energy, or can we not tell? So what do you think? Well, at a first look, we need to specify, are we dealing with any thermal energy in the system? And it's not specified, and we're aware that we can count for it. So from that standpoint, we really can't say anything about delta K because, if it's changing, delta E thermal could be taking some of the change too. And so because delta E thermal is there, we don't know really what's going on in the system. But if we do choose, let's go ahead and just choose a system in which there is no thermal energy, no dissipative forces inside the system. Even with that, can we say anything about delta K? Okay, we can't. We can't say anything about delta K. It depends on how much these are. If this work external was big and negative, then delta K would have to also decrease somewhat. If these were of equal size, delta K would be 0. If this was smaller than this one, then delta K would have to be positive. So we really can't say much about that. But we can use this to try and compare the different transformations and transfers. Okay, well, what about number 11? Okay, this one is a similar question. We can write down our energy relationship. Only this time we're said that the system's potential energy increases and the environment does work on the system. Okay, so the environment does work on the system. And so here, the potential energy increases. The environment does work on the system, which means this is positive. So the external work is always positive if it's doing work on the system. So what can we say about this? Well, again, with delta E thermal, there we really can't say anything. And even with choosing a non-dissipative system, we can't say much about delta K. It all depends on the relative strengths of these, how big the external work is, how big the potential energy is. So we can't say much about those. If work was small, the external work is smaller than the change of potential energy that's here, then we'd say that the kinetic energy would have to have gotten smaller to offset this large increased potential energy, or other scenarios are viable. Okay, let's move on to number 12. Now, number 12 is very similar in this, only uses a diagram, a bar diagram, to try and help out. So while you go look at that, I'm going to draw this. Okay, so what we have is trying to compare. It's the same thing as up here, only we've broken it up to initial stuff, or inputs, and outputs. are in what we start with and how we add to it. So that's why work is on the side of the inputs, or the initial conditions. And then what we end up with, any final states, and then thermal is always final. It only can rise. Okay, and so we're told we start with 0 kinetic, and we have 4 units of potential. And then we don't know the external work, the final kinetic energy, the final potential energy, but we do know that delta E thermal is 2 units. So how can we find what these 3 values are, work external and the final kinetic or potential energies? Well, what I do know is that the work external has to be 0, because if you look at what we're including here, the problem is about a firefighter that slides down a fire pole from the 2nd floor to the ground. Okay, and let the system be the firefighter, the pole, and the earth. So is there anything left over to do work? So this is 0 because our system included all interacting objects. The earth is what's causing the firefighter to pull down, but we've included the earth in our system. The pole would slow the firefighter down, but we've included that in our system. And we have to include that because there's a change in thermal energy between the firefighter and the pole. So that's 0, which means we have a total of 4 units of potential energy to start, or 4 units total. Okay, we have 4 units of energy to start. We know 2 of those units went into thermal energy. What happened to the other 2 units? Well, we know potential went down. Okay. Now, one thing that's a little caveat here is the gut response to say, oh, well, U final is 0 because they went to the ground. And I think that's what I would reasonably say as well, because I would assume that they measure these 4 units of energy here based on the ground being 0. Okay. But it didn't necessarily have to. This could have been relative to the 1st floor, and therefore going to the ground would be below that. Or this could be referenced to the basement, and therefore this would be a little bit positive. But if we assume that the ground is measured as 0, then that's 0, which means I'd have 2 units of kinetic energy, so that in my final state I have 4 units of total energy. All right, now think about 13. Okay, 13 is a different concept. We're comparing work and potential energy. So with the knowledge that we have about work and potential energy, or force and potential energy, if the force on a particle at some point in space is 0, would its potential energy be 0 at that point? What's the relationship between force and potential energy? So we know that force is equal to the negative of the slope of potential energy versus position, and it's the component forcing in that direction. So if this is 0, does it mean potential energy is 0? The answer is no. It means the slope, or the change in potential energy, is 0. So I know that the potential energy is not changing at that point, or at least the slope is 0 at that point. So this could be on a vertex, so at the peak of a hill of potential energy versus position, or a valley at the bottom of a valley, or it could be a flat spot, a plateau. Okay, so all these would have a force of 0 at those points. Okay, but that's all I can tell. This has a non-zero value. This has a non-zero value. That has a non-zero value of the potential. So I can't say anything about potential. Well, what about if the potential is 0? What does that say about force? Okay. Well, let me graph it again. Here is a potential energy curve versus position. Okay, and at that point, and that point, the potential is 0. What can you say about the forces? Well, the forces are non-zero at those points because the slope is non-zero at those points. We have a force this way, we have a force this way, we have another force this way. Okay, so the condition for the force or potential to be 0, it doesn't say anything about the slope, which means we don't know what the force is. Now, if it was 0 for an extended period of time, so like that, we have a plateau here at 0. Well, the slope is 0 only because of that plateau. And again, like I did up here, you can have that plateau somewhere else. And so really the only thing you can say is if the potential is 0, then only if it continues to be 0 is the force 0. All right, so that's all of our concept questions. Let's move on to our exercises. Okay, take a look at 31. I'm going to draw it while you get exposed to it. Okay, so here's our plot of potential energy versus position for some interaction. This could be gravitation. Actually, sorry, I think the problem does state what it is. Oh, well, it doesn't. So it just says one particle can move, the other particle is fixed, but this is the potential energy of the system. So what is the force acting on that particle? Okay, what is the force when the particle is at this position? What is the force on the particles at this position? So 0.5 and at 4. So how do we find that out? Think about this. So at 0.5, so Fy at x equals 0.5 is going to be the negative of the slope of the line at 0.5. Okay? Well, that's a positive slope, so I know this is going to be a negative number. And the slope is 60 over 1. So from 0 to 1, I get a rise of 60, which means I get negative 60 newtons. Okay? And then Fy at x equals 4. This is a negative slope, but I have force as a negative of the slope. So I have a negative of a negative, so I end up with a positive. And then the rise over run is 60 over 4, 5 minus 1, so going from 5 to 1 or 1 to 5, since I've already taken into account that it's negative of the slope. Okay, and because of that, I get that is going to be a plus 15 newtons. Now, graphically, I'd say that at this point right here, the force is small and pointed that way. It's positive. Over here, it's big and pointed that way. It's negative. And I can see that it's proportional to slope. Very good. Let's go to 35. Okay, so this is the idea of conservative versus non-conservative forces. So the idea is to find out the work done to get from the origin to this point here, point D, point A to point D, either going first along the x-axis to point B, and then straight up in the y direction to point D, or first going along the y-axis to point C, and then along, or in the x direction to point D, or finally just going straight from A to D. This is 3 units away, 4 units away. Okay. And the thing that we know is that the force is a vector, and it's 6i hat plus 8j hat newtons. That means as a vector, it points 6 units this way and 8 units up, which, just to pay attention, the positions here are 3 units and 4 units, so that's proportionally the same. So that force vector is in that direction. It's in the same direction simply because it's just double the proportions, and so its components form the same angle as the displacement here. Okay, so with that in mind, we want to find the work done along each of those separate paths, and then answer the question, is this a conservative force? So first of all, how do you find the work done going from A to B and B to D? All right, work A, B, D is going to be equal to the work it takes to go from A to B, which means I care about Fx delta x, okay, with this being x, this being y. And then I get to here, and then I care about Fy delta y. So work is force times its distance. So I first go this far, and so I only care about the force in that direction. And then I go that far, caring only about the force in that direction. Plugging in numbers, I have my x component of force is 6, going 3 meters, plus y component of force is 8, going 4 meters, and if I calculate that, I get 50 newtons, or 50 joules, apologize, 50 joules. Well, what about work going from A to C to D? How's that different than this one? Okay, well, first I go in the y direction, so this is simply Fy delta y plus Fx delta x. Okay, and then I just plug in my values. I get 8 times 4 plus 6 times 3, which is 50 joules. The last one is, what about going straight from A to D? Okay. Well, that means I'm going to call this direction S, so I need Fs delta S. All right, but we found out that this force right here is in the direction of S, so I care about just the full force, F delta S. All right. Now that force in magnitude, I can calculate it's going to be square root of 6 squared plus 8 squared. And that displacement from here to here, the delta S from here to here, is the hypotenuse of a 3, 4 triangle, which means that side is 5. Okay. So if I calculate this on out, I'm going to end up getting this will be 5. And this ends up being 10, if you calculate that out. 6 squared is 36, 8 squared is 64. You add those together, you get 100. That gives you 10. And so we end up with 5 times 10, or better yet, 10 times 5, because the force is 10, the displacement is 5, and that gives us 50. So we ended up getting the same work done for each of these different displacements. Okay? And so can we say the force is conservative? It seems that the force is path independent. It doesn't matter which path I go. And so we could say that this is force independent. And actually path independent. And it is actually conservative. Now I need to put in a caveat. There is a more rigorous test to be able to tell if something's truly conservative. The only way we know how to do it is to test the paths. But we technically have to test every possible path, even going from here, around here, up to there, and that's not feasible. So there is a more mathematically rigorous way that you'd see in an upper level physics class to test if it's conservative. But one thing I can conclude is every constant force that doesn't change can be path independent, and therefore conservative. Okay, so with that being said, let's move on to the last one, which is 39. Okay, go ahead and take a look at that one. I'll draw it up. Kind of getting squished there. Apologize for that. Bring that over. And our K has 4 units. Our potential has 1 unit. Okay, we don't know our work. Our final kinetic energy is 1 unit, and our final potential energy is 2 units, and our thermal energy is 1 unit. So the question is, how much work is done on the system, and is energy transferred into the system, or is energy transferred out of the system? Okay, so this is a counting up problem. Go and do that. Okay, we have 5 here, and we have 4 here. So we have 5 plus something equals 4. That ought to be a negative 1. What does that negative sign mean? It means energy was transferred out of the system, or the system did work on the environment. This is red. The environment did negative work on the system, which is better said, the system did work on the environment. So energy has left the system. All right, so that is the end of that.